Okay, today we picked up with our discussion of the conservation of energy equation. I have a fair bit of derivation to do on this, and today we unfortunately left it kind of midstream. Just give you a couple of the highlights of things that we've applied along the way, and then we'll finish it up on Wednesday of this week. First of all, just a reminder of the overall energy equation here. On the left-hand side, we have the time rate of change of energy for the system. It involves the exchanges of heat and mechanical energy externally, or separate from the internal energies of the fluid. We have the energy of the control volume, which may be evolving in time, and then we have our fluxes of energy. And same as when we talked about momentum and mass, we have our energy group here, which involves kinetic energy, potential energy, and internal energy, and then the fluxes of fluid across its faces. Rho here converts that volume to a mass. Okay, one of the first things we did today was we said, well, let's explicitly split out this work into work that's done externally by pumps and turbines. So this is work that's done by pumps or done by the fluid against turbines. And then fluid that, or work that's done internally against pressure. So this is work against pressure. And we went through a derivation where we looked at a volume of fluid that's moving along a conduit, and we found that WF dot is equal to the sum over the faces of our control volume of PI VI dot AI. Now where that arose from was P times A. P times A was the force on that face, so PI AI is equal to the force, and then velocity times distance was the work, or velocity times time was the distance over which that force was applied, and when we do that on a per time basis, in order to get the rate of work, it's just the velocity that appears. The V dot A here, I think I need a minus sign on this. Minus sign on that. To account for the fact that we're talking about the work done by the system. So the V dot A here accounts for inflows versus outflows, and you can see that it has the same form as what appears on the right-hand side of the energy equation. And that's the next step, is to group that on the right-hand side. So what we have is QH dot minus W dot, WS dot now is just the shaft work that remains, is equal to unsteadiness in the control volume, plus the fluxes through the faces of our control volume of density times, now the group inside here is 1/2 V squared, plus the potential energy term, plus let's write P over rho now, plus the internal energy, all evaluated at face I, times VI dot AI. And so now we have this group that's changing between face 1 and face 2, or multiple faces if needed. That's still the general form. Now what we're going to do, what I started today and what we'll finish on Wednesday, is considering the case of flow along a conduit with a control volume that goes between two well-defined faces, face 1 and face 2. And we're going to allow for the fact that there may be some addition or extraction of energy through QH dot, the heating, or through shaft work WS. And what we're going to do is basically connect conditions at face 1 to conditions at face 2. The one other thing I'll note in this video is just that the velocity no longer needs to be assumed to be constant over the cross-section. And instead we're going to define, so V2 varies in the cross-section, but let V2 bar equal the average over face 2. And that's sort of where we left off today. I introduced a quantity alpha, but I'll be revisiting that on Wednesday.